Welcome again to the NPTEL course on storage systems. So, we have been looking at some issues in file system design, and we briefly looked at some issues, general issues of file systems last time. Okay. So, let us get slightly more into a slightly tricky aspect of file systems, that of semantics. I think as you might be aware, file systems have grown, you might call it organically. That means that there is no specification that is given and then you go and design something for the specification. So, over a period of time various notions came around, and then finally there is some kind of standardization that happened in POSIX, so that it is applicable to most Unixes, because there is a wide variety of Unixes, and there was a need for applications to run on different types of file systems. Okay. A good example of a semantics that most of you are familiar with is the deleted but open file. Okay. This is a slightly non-standard or peculiar thing about Unix. Other operating systems do not have such semantics. Okay. And these kind of understandings have been codified into POSIX. But POSIX is basically not really, does not nail down all the details. The design committee of POSIX, to tie down too many details which will prevent good implementations, right. They purposefully leave many flexibilities and other dependencies, they just leave it, they keep it in. Okay. That is true for any specification. The idea about specification is that there has some ground rules everybody should follow, but quite a lot of it is left to ingenuity of the implementers to do better than other people. So, there is a competition between various parties who have come together to set the standard. Okay. So, because of this, the semantics is not really completely fixed, okay. And people always creatively try to exploit some feature which gives them some competitive advantage, and so in terms of sometime it becomes a accepted idiom, and finally somebody else has to, which comes later, might have to observe that idiom. Okay. That is a standard way, and this is true for not only here, but in almost every part of operating system design. I will give you one simple example. It turns out that some of you might have heard about memcopy and memmove, right. There are two different types of things. One of them handles overlapping memory regions, one does not. In one of the memcopy, for example, if you give overlapping regions, it says the behavior is undefined. So, it turns out that recently there has been a lot of there is a discussion on some kernel mailing group / Linux mailing group, that some major application like Flash, for example, has used memcopy instead of memmove, because it turns out that it breaks the semantics is broken with respect to in some implemented architecture, for example ARM or some system. And the basic issue is what is to be done about it. Do you go and tinker with glibc, do you tell the application guy to fix his code, etc. Because there are various possibilities. Now, the thing is that to get somebody to fix the code, it may not be under your control, and basically what will happen is that your Linux implementation will not be able to do Flash, let us say. That means that in the past, at least, not now, 99% of all let us say web pages, okay, dependent on Flash. So, if this particular application does not run, you may be correct, glibc may be correct. It may be that the Flash guy, the Adobe person, he used the wrong call, and it works in almost all platforms except ARM, let us say. Okay. But whatever it is, it turns out that there is no a problem on a widely used software platform like Flash. it does not work on ARM architectures. Now, what is to be done? Okay. Some people will say go and get Adobe to fix it. Some people say we do not have any control over it, you go and change it in glibc. Okay. You define memcopy to be memmove, that solves the problem. Okay. You take a small hit in terms of performance, but all your flash programs work and all end users are happy, right. So, sometimes this kind of arguments are made, okay, because finally the question is about users. Okay. Do you worry about users, or do you want everybody to curse Linux saying my flash does not work, and then they go and start using Windows or Mac OS or whatever, right. The question is, what do you do about this kind of situation, because you do not have complete control. Okay. So, it turns out the same situation happens in file systems also. Okay. If your file system design, though correct under some model, right, if it breaks all kinds of scripts, okay, then people run away from your file system and say something is wrong with the file system and go and do something else, go and start looking at something else. Okay. So, there is a certain give and take in this business. It is a bit unfortunate, even if you are right, you have to change something so that everybody is happy. Okay. Sometimes it happens. Okay. So, this is a fact of life. Okay. In commercial world, it is often happens the same thing, except that in the commercial world, you talk to the most important customer or most important few customers, take care of their reason, take care of their problems, rest of them you just drop. Okay. So that's what I'm saying, that the semantics is not really fixed typically. So it's a bit of a difficult business to be, because you are now having to support so many applications which are written by lots of diverse set of people, and then your file system can run on so many operating systems also, right, with deep device and kernel dependencies. So, you have to get it working across both these two kinds of platforms over which you do not have any control. Okay. So, it becomes slightly difficult. So, in addition to this, there is also this issue that in principle some things are inherently difficult to do. For example, copying a 1 terabyte file is not that uncommon nowadays, people do it. Copying tens of gigabytes is very common, it is nothing unusual. Even 1 terabyte, but this one, unless you have a, let us say, huge amount of memory, there is no way to give you transactional semantics for this, absolutely no way. Okay. Basically, what it means is that either it can be done, but you have to essentially use locking extensively all over the place. You cannot allow anybody else to come in between while you are copying it. So, all kinds of your file system, essentially that whole directory, for example, will have to be frozen during that time, and 1 terabyte copy is going to be, it can be multiple days. Okay. It can happen, it will be that slow, because normally you do not have, you think about it, you calculate it. Okay. So, the thing is, you can't really do this, you can do it autonomously if you are really stubborn about it, but typically it is a hopeless business. Okay. So, for the same reason, you will find that there are various things that you can do which give you very unusual results. One thing I will discuss it soon. You can try some seemingly nonsensical thing like copy a comma b and copy b comma a. This is legitimate as per the kinds of things you can talk about, though what you get is completely can surprise you. On different platforms you will have different kinds of results. Okay. So, we'll look at this soon. Okay. So, as I mentioned earlier, you need to support common idioms even if you are not in POSIX. Okay. Basically, you have to listen to your customers or your users. If you keep going against them, you lose, that is it. So, let us try to get an example, good example of this. mmap is one of the most intricate things that, one of the most difficult things for a file system to support. Okay. Basically, because once you map it, you lose complete control over that map region unless you unmap it, okay. Because you do not get any control over how that map part of the file is used. Only way you can get any control is if it faults in it, then it has to come back to the file system. That is the only way it does it. But one thing about mmap is that the protections or etc., all those things, the granularity is at the page level only. Okay. Because mmap depends on the VM subsystem, and the VM subsystem as a notion of pages, and the pages, for example, the protections or various other things are all connected with 4K or the page size only. Okay. So even if I map a file and let us say it is 10K, so you have pages of 4K each, then there will be 3 pages involved now, 4K, 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 and after 10K that will be something which is not specified what is going to be there. Typically it is zeroed, but in case you write there, the VM cannot help you to catch the bug. It cannot really fault at that point, okay, because your, let us say, validity of the page is at 4K granularity. Therefore, even if you write at 10K plus 1, nobody is going to notice. Okay. So now it turns out that for this reason, you can actually do read write past end of file in the middle of a page. Okay. Suppose you have an end of file and I can go and write after end of file, and mmap is supposed to be, let us say, cannot extend it, okay, but only the read write interface is supposed to be able to extend it. So even if you write it, it can give you, depending on your operating system, it might give you different undefined behavior. It can't really tell you what's going to happen. Similarly, you can also have after the 10K, somebody can extend it by read write interface. One is mmap interface, somebody is coming through read write interface. You extend it. The question is what is visible to users is not clear. They are also not been specified. Okay. So again, the issue is basically about when you are doing a write, do you expose the whole thing that has been written after the write is over, or do you want to give it intermediate access? Now that easy and sensible thing to do often is to say I will do it only after I finish the write. But if it is a very long write, to push for that particular way of looking at it might be difficult for some users. Okay. Like for example, I talked to you about 1 terabyte write, right. If you insist that I do it only after everything is shown, after everything is done, let us say it takes multiple days, right. It may be that I need to see something in between. One can always manufacture scenarios of that kind. Okay. So that is why various file systems do different things. There is no commonality in this, and generally the people who work with application developers, they try to figure out what their main concerns are, and they try to make sure that their concerns are handled reasonably well. Okay. That is usually what happens. Okay. And because of these things, you will find some very peculiar problems also. Okay. I am just highlighting one problem I came across in a Windows NT file server some 10 years, 15 years back. But these kind of problems are there in other file systems also, not necessarily Windows, it could be there in any particular file system. And you see the kind of, this all that you can see from the bug report. We do not have the source code of Windows NT, therefore we can't say exactly what is the problem, but this is the description given on the Microsoft page. Okay. What is the thing? It says files rapidly accessed on Windows NT file server, intermittent data corruption. That is, if you access it, too many people accessing it too fast, okay, too many requests are coming in, then there is some corruption, okay, and especially new server data files on MP systems. Okay. Now you can see why this should be the case. New server data files means basically somebody is extending the message. As I mentioned earlier, in many mailing systems, all the mail is put together in single file. Okay. When a new mail comes in, you extend it. Okay. So I can't understand it completely what this is saying, okay, because I can't understand the bug just by looking at the description given in that bug report, but one can guess that some lock was not taken. So what exactly is happening? Application performing a write extend of a file. That means a new mail message has come in and somebody is putting the next message into that huge mail file, single mail file, okay. Somebody is doing a write extend. Cache manager read ahead thread on current last page, part of larger write block. Basically there is a cache manager read, that means somebody is caching it in memory, okay, on current last page. So that means that you could have been at 10K, as I mentioned, instead of taking, of course, a much bigger file, but for the time being, let us call it 10K, okay. You are at 8K and somebody is doing a read ahead of the next page, okay. So the only two pages that are, the only stuff that is valid is 2K, right. but it is a page. So, when you are reading it, you have to have some notion of the current length of the file, and somebody is extending it also. So, as being the reader reading, the person who is reading it should have one notion of a file size, and the writer should have a different size of notion of a file size, okay, and they should keep it consistent. Okay. Now, what is being mentioned here is that while the cache manager is reading it, the write gets blocked, okay, because somebody is doing write extend. And of course, this is slightly mysterious, I can't understand it completely, but basically it says memory manager wakes up, write. So, the read ahead is going on, the write is blocked, now the write is now unblocked, it zeros last page beyond current file size, okay, and writes new data into page. For some reason, the read also zeros it later, okay. So, there is some locking problem here, I am not very clear what it is. One can guess that let us say the reader should have got the more current version of the size of the file from the writer, right, and then done something of that kind. Somehow it is not getting done, and there is some locking issue. I think that is what creates the problem. But this kind of problems are quite common. Okay, basically there is no semantics also here. Exactly what is the meaning that you have to ascribe to when somebody is extending it while somebody is reading it, right? So, so let us look at a specific example, okay, which we have some control over, because we can. Okay. Suppose I do this thing, as I mentioned, I want to look at this slightly crazy example, copy a comma b, then copy b comma a. Both are let loose at the same time. Okay. Now you can see that if there is only a single lock for a particular file, as I mentioned to you, because of what is called file control locking, FCNTL locking, you need to have lock on ranges. A database, for example, can lock 1 gigabyte part of a file, or any application also can do similar things. Okay. So, if you just have a single lock, then what will happen? You will get into deadlock, because there is a lock for A, there is a lock for B. Let us say A gets a lock and B gets a lock, then you try to get a lock for B or A, then you get stuck. Okay. The usual cross, okay, in terms of locking let us say orders. Okay. So, of course, one can say the following. You can say that this is an application problem. Okay. You can say whoever is a fool has tried to do this thing, he deserves it. That is one way to think about it. Okay. So, in essence, what you are saying is, don't do bad stuff, then I will do it correctly. But this could be there are some situations where this attitude is probably not a good one. Okay. What happens if A or B is an important file, which essentially is required for the health of the system? Okay. There are situations where this kind of things can be important, and it turns out that anyway you can't implement file systems with a single lock. In addition to the application visible lock, that FNCTL related lock, you need to also have other locks in the kernel for managing the write. Okay. So, it turns out that one way to avoid this is by using other locks possible inside the kernel, and then trying to do it and see if you can do something interesting with it. Okay. So, it turns out that there is a lock which is called the get page lock in many Unix based file systems, which also can be used as a way to avoid the deadlock. Okay. So, let us see how it happens. Okay. Now, when you are doing a copy a comma b, what normally happens in many recent Unix based systems is that A is mapped to kernel memory, and then when you do the copy, you copy from kernel memory to user memory, okay, and that is how that stuff gets into B. Okay, that is how it is done. Okay. So, how is it? Okay, let us just look at how it is done. Okay. So, the first step is map A into some reasonable place, and then you write into B from mapping of A. That is the step that is taken. Okay. One important thing is mmap is not atomic, but read write is atomic. Okay. This is another feature of some of the semantics that people have fixed now. Okay. That means that if why is mmap not atomic? Basically you map it. If there are concurrent people who have access to the same file, they have the permissions, anybody can be writing into that map region without any coordination. That means that there is no reason why anything should be atomic. That is, one guy could be writing some portion of the file partly here and partly there, somebody else can be, some other party can also do partly here and partly there. Therefore, it may not be giving that either this or that. Okay. Those kind of things may not be guaranteed. Okay. So what you do is you basically take a lock on A first, map it, and then you unlock it. That is basically the way this is done. Okay. You first take a lock on A, so that no other concurrent maps can take it at the same time. Okay. This purely to make sure you are the only person mapping it. Okay. Because if somebody else concurrently mapping it, then the system will force it to wait, and then they will look at the previously mapped things and then provide that information to the new the guy who is trying to concurrently map it. Okay. So you take a lock to ensure that you are the only party trying to map it. Okay. Then you map it and then you unlock it, so that it is now the mapping has gone through concurrently. Sorry, the mapping has gone through in a mutually synchronous manner, but the file A, for example, can be accessed by anybody who has appropriate permissions. Okay. So now what you do is you try to read from A and then copy into B. Okay. Now for B we do a RW lock on B. Okay. I said, well, this is the lock that is visible to the application. This is not a kernel only visible lock. Okay. So RW lock B is, you take the lock on B, and then now as it is copying it, what will happen is that since it has been mapped to memory, either it is already cached in memory or it will not yet cached in memory, so it will suffer a page fault. Okay. If it suffers a page fault, then you have to do what is called a get page corresponding to that. Okay. And then you do what is called UIO move. UIO move is what? It from you basically you copy it into from kernel to user area. Okay. You are moving it. Okay. So that is what happens here. Okay. So basically now the get page is what is finally again entry into the file system. Okay. This is what is again entry into the file system. Okay. So copy A comma B is basically RW lock A map RW unlock A, and then for reading B it will be RW lock B, UIO move get page, etc., and then it will continue till the copy is done, then you actually RW unlock B at the end of it. Okay. Copy B comma A also is something similar like this, right. So you will see now that depending on how these things interleave, okay, and how these things are implemented by different file systems, you get different behaviors. For example, right now when you say copy A comma B, since you have done a lock on A only for mapping purposes, after the map is done you no longer have a lock. That means somebody else can actually modify A in principle. Okay. So those things are essentially fall out from the way it has been implemented. Okay. And the reason why people do this mapping is because they find that if you do not do this mapping, there can be multiple copies of the same data both in buffer cache as well as in virtual memory. It introduces extra overhead, and it also introduces lot more memory pressure, and also can introduce consistency issues. As I think as we recollect in the previous class I mentioned that in Linux, for example, in Linux up till Linux 2.0 or 2.0, I forgot which one, it turned out that you do a write, you have to do writes to two places. You first have to go and check in the buffer, and then also check if that same thing also is somewhere in the virtual memory somewhere, and you have to write to that also. That is, every write actually is now can be two writes. one to buffer cache memory, one to virtual memory. Okay. So, to avoid those kind of overheads, you have tried to combine them together. Okay. This is what is called integrated design. Okay. And so, the mapping is what is preferred to avoid those kind of issues, but once you have this mapping, you have a variety of possibilities in terms of what can be happen during the copy. Okay. So, yeah. So, I just wanted to point out that this copy A comma B, A comma B comma is basically it is actually composed of multiple components, and how this interact decides the output what you get. Okay. And so, again this get page, for example, you get a page every 4 kilobyte blocks, typically page size. So, the copying happens at atomicity of 4 kilobytes. Okay. So, while you are getting the page from, suppose you do not do read ahead, then you will get some 4 kilobyte, copy it, and then you will again get stuck the next time, right. And then while your process sleeping, somebody else can come in and look at other things. Okay. All those things can also happen. Okay. So, that I hope that gives you some idea that the semantics of some of these file systems are slightly nebulous. Okay. It is not really that clear. So, people really want to get their semantics clear, right. They need to take extra care. They have to be very careful what they are going to do. Okay. It is not going to come just like that. And okay. So, similarly there are other issues in when you are designing file systems. For example, you have multiple execution threads, right. So, for example, there could be some kernel threads, there could be an application which comes into the kernel and does the system call, various possibilities are there. Okay. So, it turns out that oftentimes there are multiple entries through different paths, okay, to the same thing. Okay. For example, you can lock a resource and you call a lower level routine on the resource, and this lower level routine may also be called by others without locking the resource. Okay. So, the deadlock is possible if lower level routine does not know if resource is locked. Okay. So, the only way you can avoid this problem is some parameters are passed informing the low level routine about locked resources, but this is from a software engineering point of view, it is a problem, because that means that normally the lower level routine should not know anything about upper level routines, because they are sort of written in by different parties or different, they want to keep it modular, right. If the lower level routine has to know everything about all the parameters, has to be known from whatever the top level guy is doing, it becomes a problem, okay, it becomes non-modular. Okay. So, that is why people sometimes have provided what are called recursive locks. That means that somehow you keep information about who has locked it, okay, because as I said multiple entries are possible and you keep track of it, and therefore, you can probably disambiguate the situation. Okay. So, but it turns out that most kernels do not provide recursive locks. Okay. So, these are the kind of problems you have to handle in a large scale system. Okay. The thing is that you can say why people don't provide recursive locks. Okay. The standard answer could be that if you provide recursive locks, then you are adding extra code in a critical part of the locking things, and you are making everybody slow. Okay. And so, this may not be available, and you will often see the same kernel going through different designs, where somebody in the past has provided kernel locks, the recursive locks. The next iteration of the thing, somebody has decided that it is too expensive and taken it out. That has actually happened in some operating systems I know. Okay. So, so a file system also has this issue, and you can see this is quite not uncommon, because this is an example of a reasonably modern file system, the ZFS. Okay. You will see that there are multiple ways of doing the same thing. Okay. For example, I can come from like this, right. I can also come like this, right. So, I do not need to come through some of these things. Okay. I can directly come like this. Okay. So, sometimes I can some of these things, for example, I can come like this, or I can come like this. Okay. So, multiple paths by which I can get to one of these guys. Okay. And so, given the multiplicity of paths, sometimes the design becomes that much harder, because you don't know exactly how it is coming in. You need to keep some infrastructure to know which path you came through, and then only you can sort of make sense of what is going on. Okay. So, let me take a look at, let us start taking a look at some reasonably new file system. This came about, let us say, started being used about 5, 6, 7 years back, and designed by Sun, now part of Oracle. And what previously I looked at, what I mentioned previously was the older 1980s kind of modular file system. This one is a more recent one. Okay. It is an integrated file system plus logical value manager. Okay. So, it is a regular file system plus logical value manager. What does it mean? What is a value manager? It basically helps you to think of a pool of storage on different disks, etc., in an integrated manner. Okay. So that you can add a particular disk or remove a particular disk, and then somehow, as long as it is making sense, it still can, the ZFS system can give you a coherent view of the file system on whatever is available disks. Okay. Whether it is something is added or something is taken out, you still have a reasonable view without too much work on the part of the user. Whereas, if you had a non-integrated system, then you need to have two interfaces, one which you go and talk to the volume manager first, okay, and you tell that volume manager, I am adding a particular disk. Then you will have to go and tell the file system that since that something has changed, now please change something because I added something. Okay. And some of these things are slightly tricky, because if you want to add a volume, right, and then some activity is going on the file system, right, you have to now, to be able to tell the file system, please be able to use this new disk that I have added, you have to essentially get the concurrent activities in the file system to either stop or to get to a particular state where they are all in some reasonable consistent state. Then I can finally make the new disk that has been added available to the file system. File system has to now recognize it. Once it has recognized it, then it can again continue from there. So, you need some notions by which you can, what I discussed before, you can freeze the file system, add the thing, then you can thaw the file system. Okay. So, as I mentioned, something like surgery, right, you basically anesthetize the file system, add some extra limb or whatever it is, and then you say, now you go ahead. Okay. You, something of that kind has to be done. Okay. So, in an integrated file system logical value manager, this is done in a slightly more simpler way, because the file system knows about the value manager. Okay. They are not two distinct interfaces. You have to actually use a single unified set of commands to manage the system. Okay. So, basically the file system is the part ZFS, the volume manager is typically called ZPool. These two together are constitute the whole system. There is a POSIX layer, that is ZFS POSIX layer ZPL. There is a data management unit, which is basically the part which gives you the transactional semantics to the whole system, and there is a storage pool allocator. This is which actually deals with all the block devices, you might say. Okay. So, and it actually puts them together. You can request resources from it. Okay. All those things are done in this part. Okay. The ZFS, the idea has been to see if you can design fast and reliable storage using cheap commodity disks. Okay. That is the goal of the system, and basically they use a copy and write transactional object model extensively. Again, this is similar to some other models. For example, I mentioned before, NetApp has something called write anywhere file system. They also have a similar copy and write transactional model. Okay, something similar. Okay, and because of similarity here, there has been some legal cases between Sun and NetApp also for the same reason. Okay. Okay. What is interesting about this is that blocks containing active data are never overwritten in place. They are always using you are going to do copy on write. Okay. Instead, a new block is allocated and written, and then any metadata blocks referencing it. Okay. Because some data has changed, the metadata block also have to get changed. Okay. They get the original stuff is picked up and then reallocated and written again with the new information, because now it is pointing to the new block that has been allocated for the copy on write. Okay. So, because you want to have a transactional model, you also want to reduce overhead. All these multiple updates are grouped into transaction groups. You have an intent log, and then which is if you want to you basically make the changes to intent log, and then which is if you want some synchronous write semantics, then you will flush it to disk immediately, whereas if you are don't mind some asynchronous models, then the updated data structures in memory, they will start being returned to their home locations over a period of time, and then once all the home locations for a corresponding transaction are completed, then you release that space on the log. Okay. That is basically what happens. Okay. So, one of the key features of this particular system is that data integrity verification against data corruption. So, at every stage when they are doing writes or when they have to read, especially when they have to read, they check some they have some checksums and they actually check it whether it is corresponding. Okay. Each block of data or metadata checksummed, and checksum value saved in a point to the block, not in the actual block itself. Again, they keep the checksum separate from the block, it's not nearby, because if it's nearby, if there is any disk error, it might affect both of them. So, the way they have done it is that the checksum is always slightly some distance away from the block itself, and they keep what is called a Merkle tree. Basically, what it means is that you have a tree of checksums of checksums of checksums. Okay. So, it depending on the data structures, for example, if a file has got multiple blocks, you do a checksum on each block, and then all the checksums of each of the blocks are again checksummed, and then that becomes the checksum of the file. Now, we have multiple files in a directory, you have a checksum of all the files, and then any other data structures that a directory is keeping for its own management. All those data structures are checksummed, and finally, that becomes the checksum of the directory. Again, the directory is also part of other this directory is part of some other higher level directories. Again, you do a checksum on all this. Okay. So, you have basically what is a tree of checksums, this is what is called a Merkle tree, and all the way up to the root node. Okay. So, if it turns out that there is the checksums do not match, then you have to figure out where in the, you have to walk down the tree, figure out which part of it actually has got a problem. Okay. So, because you have this Merkle tree, you can easily figure it out. Okay. Because if there is a problem one side of the tree, other side is okay, then that side of the tree, the Merkle tree at the top will, what has been read and the corresponding checksum will be the same, whereas in other situation it won't be the case. So, again you have to go down one by one. Okay. So, in this particular system, there is it was designed for a 128-bit file system. So, it's very high storage capacities, okay. The pool of storage, the Z pool, is made of virtual devices, okay, and that are constructed from block devices. Because this means, what it means is that I can have different types of technologies available at the same time. For example, I can have some of it on a flash kind of device, or I can have it on a disk kind of device. Okay, they will all be virtual devices, and then I can combine them together the way I want it. Okay. They also use, because I mentioned to you earlier, this is an integrated file system and volume manager. So, they have a specific type of volume management they do, what is called RAID Z, and I will explain what this is. They try to avoid certain problems inherent in RAID 5, and I will discuss this soon. Okay. They also, in addition to RAID Z, they also have RAID Z2 and Z3. here it is tolerant to 1 disk failure, Z2 is tolerant to 2 disk failures, and Z3 is for 3 disk failures, simultaneous failures. Okay. They have some extensive caching going on. There is something called adaptive read cache. Basically, oftentimes you will find that file system load has certain locality, so LRU sort of works out very well, but there are some other situation where locality is not good, there are some streaming reads or writes going on. So, the locality issue is not good. So, ARC2 basically tries to figure out how much of the caching should happen with respect to things which have locality and how much of it for streaming. So, if for example, at any particular time there is a lot of streaming going on, this ARC2 cache will discover this fact and start giving more space for the streaming workload, okay, if that is what is dominant. Whereas, if the LRU kind of load is predominant, it will give more space for LRU. Okay. So, it is some kind of adaptive system that they have. Okay. And as I mentioned, they have a intent log and they have some other features. These are all quite common in advanced file systems. So, ZFS is no different. It provides snapshots, that is, you can take a particular view of a file system at a point in time, and then you can have multiple snapshots. So, you can also have what is called copy on write clones, that is basically you update something, you get a new copy, and then you can actually let us say you can even have what is called writable clones, that is you can essentially keep one complete fork of a particular system that has been modified. Okay. You have the original file system, then you have a slightly modified file system, and then you can start writing on that thing and have a completely let us say a branch of the original file system. Okay. Those kind of things also can be done. And it provides because NFS v4 provides access control lists, which is not there in regular Unix. They also provide this, and the encryption and decryption also are provided as part of the file system itself. And a new thing that is there is deduplication, that is if it turns out that multiple files share some common data, instead of copying it so many times, keeping so many copies of it on disk, you keep a pointer to one copy. Okay. So, those things also can be done. Okay. So, let us just look at the design. So, it has got a user level and a kernel level. There are multiple types of consumers at the user level, and then there is some structure to the kernel level. Okay. For example, the standard, the most important user of course is the file system consumer. That is a standard that's interface that we expect file systems to provide. Okay. For example, the read write interface or mmap interface, all those things. There is also a device consumer, that is many of the structures in the system you want to have it exported as a device, so that you can play around with it. Okay. For example, if there are some memory structures, for example, right, or you may want to manipulate it through a /dev interface. Okay. I think something similar to kernel memory, for example. If somebody wants to manipulate the kernel memory, for example, for doing debugging, if your operating system provides you /dev kmem, right, then through a trusted debugging routine, you can go and add breakpoints or remove breakpoints, right, and that you get by looking at kernel memory as a device and then opening the device and then seeking to the place where you want to add the breakpoint, for example, and then update at that point. Okay. So, while the kernel is going on, you can actually go and manipulate the some specific area of the kernel, it is possible. Okay. So, similarly, a device consumer, you export different parts of the file system's space, right, file system devices or structures, for example, you can export it as a device. Okay. They also have a GUI based model. I think I will skip this part, and there is also a management interface. One important thing about any complex system is that you have to provide some management applications. For example, in a standard Unix kind of system, one management application is FSCK, Okay. If something bad happens, you need to provide a way of recovering from it. Another management interface is makefs. You want to be able to make a file system in the first place, right? Also mount a file system, unmount all these things are management interfaces. Okay. So you have a management interface, and it turns out that the two main ones in ZFS are zpool and ZFS. Okay. And zpool basically handles all the things relating to creation of pools of disk. You have a lot of block devices, and you want to create virtual devices, and then you add them and remove them. Okay. The zpool provides you the capability for managing those things, and ZFS is for creating file systems and let's say mounting file systems, all those kind of things. Okay. So that's what ZFS is for. Okay. At the kernel level, there are multiple angles. One is the interface layer, for example, POSIX, right? You have to provide we have to translate, let us say, the capabilities so that the POSIX interface is available at the user level. So that's an example of interface layer. Transactional object layer, basically you want to ensure that if you have to update multiple sub-objects, how do you ensure that either all of it happens or only some other happens? Okay, you want to give that kind of semantics. That is done by this. And the storage pool layer is basically the one which worries about how to get these virtual devices, etc. Okay, how to put them together, how to, if you're interested in reliability, can you say that there has to be 3 copies of this particular let's say virtual device compared to 2 copies of some other things. Okay. So all that reliability and stitching multiple types of devices into one single common thing, all those things are done here. Again, let's just briefly look at all the things that happen here. Okay. So this is a user level, this is the kernel level. Okay. So all the regular applications which use the file system interface, they come from here. As I mentioned, the device consumer is a party who wants any of these structures, whatever is coming from here. Okay. Whatever that this path can give you, you want to see it as a device. Okay. Then the zvol basically gives you the device interface. Okay. So for example, it may be that you need to write a specific application which wants to look at the log itself. Okay. You want to recover from the log, do something. You want to do it at application level, right? So the zvol will actually manufacture for you a device by which you can actually write a program here, which actually can look at the log structures on the disk and then do something with it. Okay. As I mentioned, management applications, there is a live ZFS, and basically it in turn uses /dev ZFS as a way to talk about all the let us say waste of manipulating some of the data structures that are provided with the file system. Okay. So let's see what is live ZFS. It could be things like, suppose I want to manipulate certain pools, for example, right? There are multiple pools of storage, and then the live ZFS gives you the capability for talking about the pools, how to create a pool, how to delete a pool. If there is a pool that has got some errors, for example, okay, how to remove, for example, the parts which are bad, okay, basically because it can be composed of multiple parts. So I have a virtual device which is composed of multiple block devices, and one part of the block device has gone bad, so I can actually take this out, okay, all those kind of things. Okay. And similarly, if it is talking about file systems, then it has to basically all the mounting, unmounting, all those kind of things happen through here. Okay. Now between the user and the kernel, they all have to understand the data structures. For example, if I am writing again in the traditional kind of file systems, if I am doing a FSCK, for example, right? If I am doing FSCK, there is an on-disk data structure, and the on-disk data structure, it has to be used for your FSCK application to be able to parse it, right. That means that there is some set of data structures that are common between the user and the kernel. Okay. So, these things have to be included in both the kernel code as well as in the user application code. Okay. They have to be identical. Okay. So, so some of those things are exported through they are included in many of the programs that are being used by Lec-24 ZFS. Okay. Now, there is also something called I told you this is the POSIX interface, and that is where all the vnode operations get done here. Okay. As I mentioned to you earlier, there is typical Unix file systems have a file system independent layer, and they manipulate something called vnodes, virtual nodes, whereas the physically realized nodes are called inodes. In ZFS they are called znodes. Okay. And basically what happens is that by the time you come here, you have already gone through the vnode the VFS layer and has finally come to this point. Okay. And to do some of these file system operations, it has to use the intent log, so for the logging, etc. In addition, it uses, for implementing directories, uses something called ZAP. Basically, this is a ZFS attribute processor. Okay. Basically, it is metadata, how to, anything to do with metadata, for example, or directories is being handled here. Okay. And okay. Now, there is also this I mentioned data management unit. This is the one which actually is involved in the transactional semantics, providing the transactional semantics. Okay. And because you can provide snapshots and clones, again all this come from this side. Okay. The management application, because you can, because the system administrator sits at the terminal and basically types in saying create a clone for this. That comes the management interface. Okay. So, all these clones, all these things are managed through this part. Okay. And this part requires the transactional layer, transactional part of the system, so that you can keep different, as I mentioned, this is a copy and write transactional model. Okay. So, anytime you do a snapshot, etc., you need to have copy and write, and so that actually interacts with this transactional part of the system. Okay. You can also have traversal. What is this traversal? Basically, it is a way in which you can look at different types of clones and snapshots. Okay. There is a hierarchy amongst all these things, because I start with a file system, I have a, if I do copy and write, I get one version of the file system, a snapshot, even that finally also can be snapshotted. So, there is some kind of a tree of snapshots, etc. Okay. And there is a lot of sharing going on between various versions of it. So, you have to traverse this particular tree to figure out where the block actually is. It may be the block what you are looking for could be at the topmost level, because you recently updated that one, or it could be that it is there in the lower level snapshot layer, or it may actually be present in the original file system itself. So, you have to do the traversal on the file system. So, again you can start seeing why what this is. Basically, /ZFS gives you the ability to talk about all these different types of snapshots and clones and other things, because you need to have a name to each of these things, right. So, you provide that naming, etc., through /ZFS. Okay. This is the cache. Again, this is the part which is concerning closer to the, in the older systems we are talking about buffer cache. This is closer to the buffer cache part of it. That is why the cache is out here, and this is the part which actually splits a large IO into smaller parts, and then since it has been split into smaller parts, if it actually tries to see if all of the parts are complete, those kind of things, it actually waits for subtasks to finish, all those kind of things happen here. Okay. So, the VDEV is basically a virtual device. So, it is basically what you might call as a pseudo device, because it can be using RAID etc., right. You can construct a logical device or a virtual device composed of physical devices. Okay. And then this is what they call a layered device interface. This is the final thing that finally talk to actual device. So this is some other kernel infrastructure, the device driver infrastructure, which is used as a way to talk to the file systems. Okay. You'll also notice there is a configuration here which goes through all these things. Okay. This configuration goes to vdev, goes to arc, goes to traversal, etc. Okay. So, so you can see it's a fairly complex infrastructure that's out here, and it will it's non-trivial to get most of these things work correctly, given all kind of concurrency, given the demands of the user with respect to the interface they demand, which are changing over periods of time, the devices are changing over a period of time. All kinds of complications are there. That's why designing a file system is a reasonably complicated business. It's not you don't see new file systems every other day. Okay. For example, when you talk about architectures, right, you'll see that people can come up with new architectures quite fast, but somehow that same level at which the speed at which architectures come out, you don't find it here. Okay. Because in the case of architectures, even that we have similar problems, but the instruction set sort of isolates the complexities. Okay. Of course, there is a small if you talk about things like memory models or etc. There are issues there also, but this one is a bit more tricky because all the applications are out here. You have to satisfy all the applications, and the applications are written by large numbers of people. Okay. Whereas hardly any guy usually directly manipulates instruction sets. Okay. So in a sense, the reason why it is more complex is because the numbers of applications that you have to satisfy. Okay. That makes it more difficult. Okay, I will continue a bit on this next class.